So, as I announced in the previous class, I posted the second homework assignment. And then the homework assignment covers what we learned in chapter 2, the instruction set architecture. So usually in homework assignment number 2, so the questions are asked about the RISC-V assembly instructions and how to write the assembly code, and then how also the question is about how the students understand the assembly code, the RISC-V assembly code. Okay. So please try to solve the homework questions by yourselves. And then I believe it's very important. So actually, so every semester I said that the level of the midterm or final exam questions are very similar to the homework questions. But everyone said the questions in midterm or final exams are more difficult. But I don't think so. So I think the difficulty level is similar to the homework difficulty. That means the questions in the homework assignment. So try to solve the homework questions by yourselves. It's so important. Okay. So in the previous class, I covered how a compiler works, and then actually before explaining about the compiler, then I also covered some additional RISC-V instructions such as AUI. So AUI supports the very large constant number, and then with this AUI, so we can generate the large constant number easily. Okay. And then also we discussed about some additional format, instruction format of the RISC-V instructions, like SP format and UZ format. And then, the conditional branch instructions use the SP format, and then jump instructions, like jump and link instructions, use UZ format. Okay, so I summarized some encoding rules of the RISC-V instructions, and then we learned how compiler works. So actually, so it's not a compiler class. So this course is not a compiler course. So actually, you need to learn the detail of the compilation in the compiler course. Okay, so but I briefly explain how the high-level language codes are compiled by compilers, and then okay, so and then you need to understand why compiler optimization is critical for the performance. Okay, so in the chapter 1, we learn how to measure the performance of our computer systems. So actually, the performance is the inverse of the execution time. So we can calculate the execution time while running some applications on the target computer systems. Okay, and then execution time is determined by instruction count and CPI and clock period. And then, as you can see, the clock period is the hardware part. So it's related to the hardware implementation and then structure of the processor. But compilers can change instruction count and CPI. So these graphs shows how the instruction counts and then CPIs can be changed by compiler options, so compiler optimizations. Also, we can increase the performance of the application with compiler optimization techniques. Like So this is the example of the GCC, and then as I explained, we can assign additional optimization level for the GCC. So then as you can see, so this is dramatic. So performance can be dramatically improved by compilers also. Okay, it's so important. Also, we learned that the performance of programs, applications can be changed by programming languages like C, Python, not Python, Python is interpreted language, C or Java, and then some other compiler-based languages. Okay? Now, I believe usually the C is the most powerful programming languages because C is the kind of C is also the high-level languages, but C also can handle some low-level, so low-level part of the computer system. That's why the C is the powerful programming language. And then if you are interested in the system programming, such as the firmware or operating systems or some device drivers, then you need to know C. Okay, because these applications usually are written in C, not other languages. And then, as I explained, with C, that we can also handle the low level, so it's a system level or some low level part of the computer systems. So that's why the C is very critical for some system programming and then firmware and device drivers. Okay, and then I will briefly explain about some arrays and pointers. So I believe someone remembered that I frequently use the AND operator. This AND operator is the operator in C. And then if this AND operator is used before some variables, then this means the address of A. And then C has the pointer type. So actually the pointer means the address of some variables, like some variable. Okay, so we can access some data stored in the variable or some arrays with the pointers. Because if we just declare the pointer with the int pointer p, then this pointer stores the address, just the address. Okay, so we can think that a pointer is just the address. So and then we can access some memory space with a pointer. Okay, so which means that if we declare the array, some arrays like ARR, like 10. So if we declare arrays like array 10, then which means that this array includes 10 elements. And then we can access each element with the index of the array. So this is called the index. We can also access some array element with the index number. Okay, like array 0 and then array 1. But we can also access each element of this array with a pointer. Okay, so that means that if we just know the address, the base address of an array, then we can access some other elements in arrays in the array with the pointer, like with the address. Okay, so we can write the code with the array type, and also we can write the code with pointers. Okay, so actually these two programs, actually these two programs are equivalent. So that means that the operation of these two programs are the same. Okay, but the left part use the just array. So receive the array type, and then when the array is indexed accessed by index of this array, and then the right part program is somewhat different. So as you can see, the right program, actually the right function, receives the pointer as an argument. Okay, and then as you can see, the pointer is declared inside of this function, and then we can access some you can access some element of an array with the pointer like this. Okay, so as you can see, you can find the AND operator before the first element of the array, so which means that it's the base address of array. Okay. So actually, these programs are the same, and then also we can access some data pointed by this pointer with this star operator. Okay, so it's the same thing. But if these programs, actually these functions, if these functions are compiled, then it can be compiled to some using different instructions. Okay, so if we just use the array type data, then we need to calculate the index of array. And then actually, we already know that only the load instruction or store instructions can access data in main memory. And then array data exists in main memory. And then in order to access these elements of array, then we need to calculate the address of each element. Okay, and then in order to calculate the address, so this program calculate the address of each element with this instruction, add instruction, and then as you can see, it's just this function just initialize each element of an array with 0. So and then the store instruction store some target memory space pointed by this address, and the address is calculated by this add instruction, and then store 0 values to the target address. And then as you can see, this is the iteration loop. Okay, so this part is repeatedly executed by branch instructions. Okay, now how about this? So as you can see, so the address is also calculated, but in this as you can see, firstly, there is a right function. The first calculate the base address, and then add the address from this base address with the size of element of array. Okay, so initialize the base address here, and then when the loop is iteratively executed, then we just add the size of the element A. So what is different actually? So I already said that these two functions are equivalent if we just compare the operations of these two functions. So what is different? If we just compare this compiled assembly code, then what is different? The instructions are different, is right? Then which one is better? So my question is that which one is better?
Pointer.
Pointer version? Why?
Because the assembly lines in the loop is smaller.
Badly.
그러니까 룹 안에 있는 명령의 개수가 더 적기 때문에
Yeah, that's right.
더 효율적일 것 같아요.
So, yeah, right. So he said that the number of instructions inside of this loop is smaller. So why is better? So if this number of instructions is smaller, then why is it better? Because if this function, this iterative loop is executed, then the instructions in this loop are executed. So which means that if this function is executed, so this is the instruction number 1, and then as you can see, we can find that there are 5 instructions in this loop. So the number of instructions in this program is the 1 plus 5n. So n is the number of iterations. And then if we just compare the number of instructions of this right function, then we can find that this is the 3 plus 3n. The n is also the iteration number. And then if the iteration number is large, so not large enough, then we can say that for number of instructions, if we just compare the number of instructions, if for the large n, so we can easily know that the right function has smaller number of instructions. And then for execution time is the instruction count multiplied CPI multiplied T. And if the CPI is the same, then instruction count determines the performance. So that's why the right code is better. So another question, then do we need write the code with pointers? So actually the pointer is some tricky part in C language. Actually, every student think that the pointer is the most difficult part in C. So do we need to use pointers? So actually not. You don't need to worry about the pointers actually. So the good news is that actually the compilers. So if we just translate this code directly, it's just 1 by 1, then the compiler may generate the assembly code like this. It's an unoptimized version. Also, compilers can generate the code like this for some pointer version. But compiler also applies some optimization techniques. So even though we use this array version, compilers generate a good code. So it means that some optimized code. So even though we use some array version of this code, then compilers can generate an optimized code like this here. So usually we don't need to worry about the optimized code in C. But sometimes for the system programming, if we just write some firmware code or device drivers or some specific system applications, then we may need to use some assembly code directly. Also, we may access some data in the memory with the pointers. Okay, so if you know about the pointers, then that's good. But the good news is that we don't need to use pointers for every code actually, because the compilers can generate the optimized code. Okay? But we can compare the performance of these two different compiled codes like this. So we need to distinguish, oh, it's the right version, it's the better version, okay? Then, oh, it's good. It's done. So we cover the RISC-V instructions in chapter 2, and then I briefly introduced the x86 instructions. So actually, the x86 is the most popular ISA because the Intel and AMD makes the CPUs that use the x86 ISA. So most of the laptop computers or desktop computers and server computers use the x86 CPUs, x86 ISA. Then, actually, the x86 was invented by Intel a very long time ago. And then, as you know, actually we learned about the RISC-V. Then, as you can see, the RISC-V includes the RISC, so which means there is the RISC type ISA. But on the other hand, the x86 ISA is the CISC type. And then if we just compare the name of this RISC and CISC, then the R of the RISC means the reduced. So it means the reduced instruction set. However, CISC means C of CISC means the complex. So if we just compare the name of the RISC and names of RISC and CISC, then we can guess that CISC type instructions are complex ISA, and then x86 is the CISC type ISA. That means that is the very complex ISA. And then if we just compare some instructions of RISC type like ARM or RISC-V, and if we just compare the instructions of RISC-V and x86, then we can find that x86 is very complex. It's a very complicated. But x86 instruction set architectures are widely used for desktop CPUs and then laptop and then server CPUs. So we can briefly check some property of x86 ISA. Okay, but recently the Apple was also the very popular computer manufacturer developed their own CPU called the M1, and then as you know, the M1 uses the ARM ISA, not x86. So currently, the Apple is making the laptop computers or some desktop computers that use ARM ISA. Okay, but most of the server systems use Intel or AMD CPUs. So x86 is the most popular ISA. Now let's see the history of the x86 ISA. So this is the very old CPU, 8080. It's the 8-bit CPU. So actually, as I mentioned, the x86 ISA is the very old instruction set architecture and developed by Intel. So Intel just invented the 8-bit microprocessor. It's the first 8-bit CPU, and then it's called the 8080. And then as you can see, in 1974, it's a very long time ago. And then Intel also made the 16-bit CPUs called the 8086. And then also Intel made the 8087. And then Intel included the floating point processor. So 8087 includes the floating point coprocessor. So which means that 8086 just includes the integer type ALU. So which means the 8086 just supports the integer type instructions like RISC-V I version. But in 1980, Intel also include the 8087 is the floating point coprocessor. So coprocessor means that so there is a CPU, and then coprocessor is attached beside the CPU, and then the floating point instructions are given to the CPU. The CPU sends these floating point instructions to the coprocessor, and then the result is computed by this coprocessor. So it's very similar to the GPU, because currently the CPU is the main processor, but for gaming or image processing, we use GPUs. But GPUs are coprocessor, not a main processor. But interesting is that in 1980, floating point units are computed by coprocessors. Okay, so it's very interesting. And then so Intel developed the 8286 stuff, and then 8286 support the 24-bit address with the memory management unit. Okay, and then so the 8386 is the 32-bit extension of the Intel x86 ISA. So which means that it is the 32-bit instruction set. It's similar to the RISC-V IV 32I. Okay, this is the 32-bit instruction set. So Intel supports the 32-bit instructions with the 8386. Okay, it's called the IA32. That is the some base instructions of Intel 32-bit computers. Okay, and then Intel developed the I486, and then so Intel developed the Pentium, and then Pentium supports the superscalar, and then also supports the 64-bit data path. And then Pentium Pro, Pentium 3, Pentium 4, and then as you can see, Intel includes the more instructions. So if you see that this some history of the Intel processors, so we can find that the SSE, this is the SIMD extension, and then we use this SIMD extension instructions for multimedia applications. So that means that Intel includes the more instructions in their CPUs. So which means, so originally, this is the 8-bit computers. So there were a small number of instructions for this old type CPUs, but Intel added more instructions in some advanced version of the CPUs, like the i486, and then Pentium, and then Pentium Pro, and Pentium 3. So as you can see, Intel includes some more instructions. Okay. So now, we are using, Intel is developing the core architecture for the core i3, i5, i7, and even i9. Okay, and then we can say actually the baseline instruction set architecture of the Intel x86 is the IA32. This is the 32-bit instruction set, and then actually this 32-bit instruction set just support the 4 GB of memory. It is because with the 32-bit data set, you can just so you can easily calculate. So actually 10-bit is the kilobyte, 20-bit is the gigabyte, and the megabyte, and then 30-bit is the gigabyte. So with the 32-bit, we can just support the 4 giga, because 30-bit is the giga, and then additional 4 is giga, is 2-bit. Okay, but we actually need larger memories. So that means that we need to also actually the computer systems need to support the larger memories. Which means that the instructions need to support the larger bit resolutions, okay, like a 64-bit. So actually, the 64-bit x86 ISA was developed by AMD. So AMD developed the AMD 64. So this is the extended architecture. So this is the extended x86 instruction set architecture that supports the 64-bit data. And then, so that's why if you are interested in Linux operating system, you can find that some applications that is compiled by 32-bit instruction set has some postfix like I386 because 386 is the supports as 32-bit extensions firstly. But if the application is compiled by 64-bit instruction set, and these applications have the postfix like AMD 64 because 64-bit instruction extended instructions are developed by AMD. And what did it do? So actually, the Intel originally developed the x86 ISA, but 64-bit extensions are developed by AMD. And what did Intel do? Intel tried to make the very new ISA called the actually IA64. And then Intel also generated the new CPUs using this new instruction set architecture because Intel thought that x86 are very complex because Intel needs to support the backward compatibility. Because the x86 has very long history, so and then new instructions are added again and again and again. So it means that the instructions are very dirty. So the instruction set architecture is very dirty, and then very inefficient. So Intel tried to make a new instruction set architecture called the IA64 that supports the 64-bit instructions, 64-bit data. So Intel also made the new CPUs called Itanium. But these new CPUs failed in market. Why? Because of backward compatibility issue. Also, Intel thought that Intel believed that with the compiler optimization, then they can improve the performance of the computer system. So which means that Intel tried to make very simple processors, and then with the compiler optimization, then Intel believed that the applications can exploit these simple architectures efficiently. But it was very hard and it was very difficult, and then also because of the backward compatibility issue, actually the Itanium failed in market. So actually Intel dropped this Itanium CPUs maybe I think it's 4 years ago. So IA64 failed also. Okay, so the lesson is that IA64 was the good ISA. It's a very clean and then efficient, and then also with the IA64 you can build very simple and then efficient CPUs. But technical elegance does not connect it to the market successes. Okay, so because market is selected by customers, then customers selected some compatible CPUs like AMD 64. Okay, so this this slide shows the basic x86 registers. And then in RISC-V ISA, so we learned that RISC-V has 32 general purpose registers. But as you can see, the x86 registers are a little bit different. x86 just support the 8 general purpose registers. Also, x86 support the some special purpose registers called the CS, SSDS, like something like that. Okay, so which means that so x86 architecture is also is different from RISC type registers. Okay. Also, in a RISC-V, we learned that the data in main memory can be accessed by only data transfer instructions like load instructions and then store instructions. And then in order to use the data in this main memory, this data is transferred by load or store instructions first, actually by load instruction. And then this data is transferred to the register file first. And then using some arithmetic or logical instructions, we generate the outputs by the simplified operation. And then these outputs are also stored in the register file. So, and then in order to update the data in the main memory, then we can use the store instruction. That is the feature of RISC type ISA. But CISC is a little bit different. So the CISC supports the very complex data access methods. Also, the CISC supports the very complex addressing mode. So, which means that if we just think of like the add instruction with the CISC type and like the x86 instruction, the add instruction can access the also data in main memory. Also, it supports the very complex addressing mode. Okay, so it's a different. Okay. Also, the size of the instruction. x86 also exhibit a very complex encoding rule. And then in the chapter 2, we learned that RISC-V, the size of the instructions in RISC-V is 32 bit. So as you can see, x86 instructions have variable length. Okay, so it's very difficult to decode the instructions, x86 instructions. Okay, but so this is disadvantages of CISC type ISA. So which means that the decoding is also complex, the instructions are complex, the addressing mode is complex. And then actually the good thing is if we just use the CISC type ISA, then we can reduce the instruction count. Why? Because think like this add instruction. In order to calculate the C equal A plus B, and then let us assume that the data of this data of A, B, C are in main memory. And then in order to compute this C equal A plus B with the RISC type ISA, the data should be transferred to the register file first with the load instruction. And then we need to use the add instruction, and then also we store the result with the store instruction. So like load, add, store instruction. But if we can, the add instruction can access the data in main memory directly and with the CISC type ISA, then we can just use this add instruction only. Which means that with the RISC type ISA, we need to use the 4 instructions, but with the x86 ISA, then we can just use the only 1 instruction. But hardware complexity matters. So if the hardware is complex, then the performance of the hardware is reduced. Also, it's very difficult to build hardware, so like C processors with the complex instructions. So Intel or AMD also knows that RISC type ISA is better than CISC type ISA because RISC type ISA is simple, and then if the computer processor supports the simple ISA, then we can build the simpler processors. But problem is that the Intel or AMD need to support the x86 ISA. Also, in order to build some new CPUs, these new CPUs also support the very old instructions, very inefficient old instructions. So how can we support these instructions? So, means the Intel or AMD currently builds the RISC-like processors, like ARM or RISC-V processors. But CISC type instructions, like very complex instructions, are decoded into multiple simple instructions, like RISC type instructions. And then these multiple instructions are executed by these RISC-like processors. That is the how the Intel or AMD is the very efficient processors. So processor just supports the very simple instructions, then we can build a very efficient hardware. Is the good thing. Also, we can easily improve the performance of these CPUs or processors. And then the complex instructions are just decoded into multiple simple instructions. So these simple instructions are executed in these RISC-like processors. So we can say, so we can compare the RISC type computer or CISC type computer, and then RISC is the more simple, and then CISC is the more complex. But recently, most of the processor has the RISC-like architectures. Okay, it's very interesting. Okay, so in the chapter 2, we learned about the RISC-V ISA, and then how this RISC-V ISA was designed, and then also we learned how the RISC-V instructions are encoded into the machine code, and then also we learned about some encoding types or encoding rules of RISC-V. Also, we learned about some various classes of RISC-V instructions, like arithmetic or data transfers and control instructions, and so on. So okay, so these different classes of instructions are required for supporting our high-level language code. Okay, high-level language codes are compiled using compilers, and then compiler generate the assembly instructions, and then assembly instructions are encoded into the machine code or machine instructions. And then in order to support some specific operations required for high-level language code, the ISA, the instruction set architecture, defines some instructions, the required instructions. Okay, and then we can build the computer hardware based on these instructions. Okay. Okay, so okay, we can go to the next chapter. So now we are in chapter 3, the arithmetic for computers. So In chapter 2, we learned about the instruction set architecture, and instruction set architecture is the interface between software and hardware. Okay, so in the instruction set architecture, instructions are defined, and then the result of each instruction is also defined. Then hardware engineers need to build some processors that supports these instructions. And how can you build the hardware? So we will learn how to build the control processors in chapter 4, and then we will learn about the memory systems in chapter 5. And then, but before going into chapter 4, so it's a hardware. In chapter 4, we will explore the hardware architecture, like pipelining. But before going to the chapter 4, in chapter 3, we will learn about how to build arithmetic units in computer hardware. So, for example, think like the add instruction, okay? Add instruction. So, in order to support the add instruction, like add x1, x2, x3. So, we in chapter 2, we learned that the add instruction requires the 2 operands from registers. Right? So, which means that the registers just store the 64-bit data, 64-bit binary data. Right? So, if the x2, the data is read from x2, then 64-bit binary data is read from the register file. And then another 64-bit binary data is read from the x3. And then we need to perform the add operation. Then result is generated. And then in chapter 3, then we will learn how to build this part and how to build the add or sub, like or multiplier or divider in computer hardware. Also, in chapter 3, we will learn how to represent the floating point numbers. So what are floating point numbers? So we are very familiar with the integers, because so in a computer system, integer means just a binary number, right? The binary number means that it's the number is 2. Then what are floating point numbers? Floating point numbers are so in Korean, the floating point numbers are called 소수, which means it's very similar to the real number. So we can represent the floating point number like 1.2, 3, 4, 5, like this. So, but with the integer type number, you can just represent the integer type like 1 or 2 or 3 or -1, -2. So it's an integer type. But we also need to represent the floating point type numbers. And then we will learn how to represent the floating point numbers in computer systems. But if you are familiar with C, then you can, I believe you can know the data type called float or double. So when do we use these data types, float or double? You know, if we want to use the floating point numbers, then we use these data types, which means that the C also distinguishes the different data types in the computer system. So if we just use this float or double data type, then that means we can use the floating point numbers. Okay. And then I believe some of you took the digital logic design course, and you are familiar with these arithmetic units, because I believe some of you just already learned about how to build arithmetic units such as the adders, subtractors, and multipliers. Okay, so I briefly explain. Okay, So how can you implement the addition? Well, in decimal number, so how do we perform the addition in decimal number? 1, 2 plus 2, 3. So for the decimal number, for the addition, then we just perform the add operation for each digit. Okay, and then if each digit, if some digit generate the carry, like if the result of this digit is bigger than or equal to 10, then the carry is generated. So it's not a good example. Like 19 plus 23, then there's a 2, and then carry is generated like here. And then it's the same to the binary number. So it just performs the add operation for each digit of the binary numbers, and then carry can be generated for this digit. And if the carry is generated, then carry is added to the next digit of the binary number. So, but add operation is very simple. So it's like so when you learn about some arithmetics in the elementary school, then add or solve is easier than the multiply or divide, right? And the also system is that the add, addition, or subtractions are relatively simple compared to the multiplier or multiply or divider. Okay, so and then but when you perform the addition, then we need to consider the underflow or overflow. So, and we frequently use the same word, overflow, which means that we just use the 2's complement signed number for the integer type data. So, which means that the size of the data is fixed. So which means if we just add the very large numbers, very large numbers, then the result will be may exceed the 64-bit, the allowed number of digits of the 64-bit data. Then the result may be incorrect. So in this case, we need to detect the overflow. So overflow means that, so it's actually the detection of the overflow is simple, because if we just perform the positive number plus positive number, but if the minus negative number is generated, then it's the incorrect result. Then the different case is the same. The negative number plus negative number, but it may generate the positive number. In this case, this result is incorrect. So by comparing the sign of the two operands and then the sign of the result, then we can detect the overflow easily. And then if overflow is detected, then the computer process, the computer hardware, just report this overflow error. Okay? So kind of exception. Then subtraction. Subtraction is simple. So it's like, actually the subtraction is the same to the addition, right? So 7 minus 6 is actually 7 plus minus 6. So subtraction is just an addition of negative number. Okay? So how can we implement the subtractor, like sub x1, x2, x3? How can you implement? So it's the definition of this sub instruction is x1 equal x2 minus x3. So which means that we can negate the data in x3 simply. So it's like x2 plus minus x3. can we negate this data? It's also simple because we can negate this data with the inverse of each bit and then plus 1. So actually, we don't need to implement the subtractor. If we just implement the adder for the some 64-bit data, then we can easily implement the subtractor by adding negation logic. Okay, like inverse of each digit and then plus 1. Okay, so it's very simple. Okay, so let's skip to this part. And then multiplication. So, and then I think the multiplication is relatively difficult compared to the addition or subtraction. And then it's the same to the decimal numbers like 1, 2, plus 2, 3. So how can you calculate this multiplication? You just perform the multiplication for this digit. So this is called the multiplicand, and then this is called the multiplier. So, and then the multiplication is performed for each digit of a multiplier. So we perform the multiplication for the 12 multiplied by 3, so 36. And then another multiplication is performed for the next digit of a multiplier, like 24. So multiplication is performed for each digit of a multiplier, and these results are called partial product. So it's not a final result, it's a final product result. So it's the result of partial multiplication. That's why these numbers are called partial product. So partial products are computed from each digit of a multiplier. And then we just add the generated partial product to generate the final result, 276 here. And it's the same to binary number. The binary number is the same. The multiplication is performed for each digit of a multiplier, and then partial products are generated like this. But for the binary number, the multiplication is very simple because if the digit of multiplier is 1, then we can just repeat the multiplicand. But and then if the digit of the multiplier is 0, then it's just 0. Then we can just add the non-zero partial product of this multiplication, and then we generate the final product. Then how can we implement this multiplication? We can implement the multiplication logic like this simple multiplication method, which means you can just perform the multiplication for each digit of a multiplier, and then firstly he performs the multiplication for the LSB of multiplier, and then for the next digit the partial product is generated, but we need to consider the location of the digit for this multiplier, right? So which means that when the partial product is generated for the next digit, then we need to shift left this partial product from the second digit of the multiplier. So actually there is 0 here, and then for the second digit, it's shift left by 2, shifted by 2, and then 0, 0, 0. And then the partial product is generated, and then these partial products are accumulated. That means they added again, again, again. Okay. So this is the hardware of multiplier, very simple multiplier. So which means that actually the multiplicand is shifted, and then this multiplicand is multiplied by digit of the this multiplier, and then the partial products are accumulated here. Okay. So this is the hardware structure of the multiplier, and then this the video shows the flow chart of the multiplier. But what's the disadvantage of this multiplier? What is the disadvantage? So I said, so actually the add is very simple. Adder is very simple. So we can say that with the adder can complete its operation within 1 clock because adder is very simple. But if we just calculate the multiplication like this way, like the multiplicand is shifted, and then it's the partial product is generated, and then it's accumulated, and then shifted, and partial product generated, and then accumulated, which means that it will take long time, right? So actually, if we just implement the multiplier like this, shifted, productive, shifted, productive, shifted, productive, and then accumulation, and then if accumulation is just an adder, is an adder. So which means that this addition may consume the 1 clock, and then which means if we just perform the 64-bit multiplication, and it may consume 64 clocks. Right, so shifted, add, shifted, add, shifted, add. It's not good for the performance. So, but actually the good things in the multiplication is that we can perform this partial, the addition of a partial product in parallel. That's right. So we can parallelly generate the partial product for each digit of the multiplier, right? In parallel. So if we just make invest more hardware, and we can calculate we can generate the partial product in parallel way. And then generated partial products are just compressed. So which means that the multiplier may generate so if we just use the 64-bit data, may generate the 64 partial products. Right, and then these 64-bit partial products are added again and again. So we can, in a simple way, we can build a tree-like adder, like partial product 0 is added to partial product 1, and then some new partial products are generated, and then blah, 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 blah. It's a simple way, but we can also apply some more fancy algorithms for the addition of the partial products. So usually, this is the very simple hardware, and then this simple hardware shows the very low performance, but we can generate the best multiplier. So it is possible because, as I mentioned, we can compute the partial product in parallel. So we can also perform the addition of the two partial products also in parallel. If we just invest some hardware, okay? So actually the multiplier is good. Okay, even we use the best multiplier, and multiplier takes the more cycles than adder or subtractors. Okay, because we require many adders or many adding steps for the multiplier. And then risk 5 also supports the multiplication instructions code like this, some more, and then for HQ like this. So, but another property of the multiplication is that if we just multiply two-digit number, multiply two-digit number, then it will generate the 4 digits, right? In the decimal number. It's the same to the binary numbers. So if we just perform the 64-bit multiplied by 64-bit, and then this will generate the 128-bit result. So, but we are running about the 64-bit computer, and then which means that every data is a 64-bit. How can we store the this 128 result? So RISC-V supports the true multiplication instruction, like simple multiply and then mod H. So which means that mod just stores the lower 64-bit of the product, so it's the final result, and then mod H stores the upper 64-bit. So 128 bits of final result is generated by multiplier. We just split this result into the two parts, like lower part and then upper part. And then lower part is stored as some register, and then the upper part is stored in another register. So RISC-V supports these two multiplication instruction. Also, we can use the unsigned number or signed number. So, and then actually the sign of the this final result is determined by upper part of the final result. So actually what RISC-V distinguishes the sign of the operands of multiplication. Okay, like more HU or more HSU. Okay. And then division. So division is the project process of the multiplication actually, but division is more complex than multiplication. And the same to the also decimal number. So how can we compute the division in decimal numbers? Like 24 divided by like so small. 1, 2, 3 divided by 19. So how can we compute the divide in decimal number? So we just check the, this is called the divisor, so here, the divisor, and then this number is called the dividend. Dividend means that is the number which is divided by divisor, okay? So how can we compute the division in decimal number? We just compare the we just compare the magnitude of this dividend for the same digit of the divisor. So we just compare the 12 with 19. And then if the 12 is bigger than 19, then we can generate the quotient. So 뭐죠? Quotient here. But in this case, the 12 is smaller than the 19. So actually the quotient is 0. Then, because the quotient is 0, then we just compare the 19 with the 123. So in this case, we can just generate the quotient like 6, right? And we generate the 19 multiplied by 6, and then and then the remainder is calculated from binary, and then quotient is calculated like this. And it's the same to binary number because it's a division. The division is the same to the binary number. So how can we compute the division in binary number? So this is the dividend and this is divisor. And then as you know, as you can see, the digit of the divisor is 4 bit. So we just compare the 4 bit of the upper 4 bit of the dividend with the divisor. Which one is bigger? This is bigger. Okay. And we can say that, oh, this is the quotient for this part is 1, 1, 0, 0. And then this is subtracted from the dividend. Then this is new remainder. And then 1, 0 is compared with the divisor. And then we can say, oh, 1, 0 is smaller. So quotient is 0. And then 1. So finally, we need to compare the 1, 0, 1, 0 with the 1, 0, 0, 0, 0. So final quotient is 1. And then this remaining value is becomes the remainder. So when the division is computed, then we need to generate the quotient and remainder. Okay, so 나머지 and 목. So this is how the division is computed in binary. It's the same to the decimal number actually, but it's not easy to implement the fast divider. Why? When I explain about the division, I said compare, and then if the dividend is larger than the divisor, then minus. It's a subtract. And then if not, just if the subtraction is not performed. So when the division is performed, it's like a compare and minus. Compare and minus. And then if the comparison is inserted in some operation, it's not easy to write a parallel operation. So that means that it's not implement the parallel logic because we need to compare and perform something. Compare, perform something. And so it's blocked. So good thing of the multiplication is that we can perform the multiplication for each digit of the multiplier in parallel. But division is different because we cannot parallelize this division operation. Right? Compare, subtract, compare, and subtract. And then this subtraction is determined by result of comparison. So actually, implementing the fast divider is very difficult. So if we just compare the flow chart and then, well, actually, if we just implement a very simple divider, like a simple multiplier, which consumes the 32 or 64 clocks, and then we can implement a simple divider like this. So we just compare the divisor with the dividend, and then shift and performs some subtraction, and then shift, and then also compare, and then subtraction is performed, and then shift here. So it's similar to the simple multiplier, but but this advantage is that as I explained in the simple multiplier logic, simple divider logic will consume many cycles. But it's very hard to implement the fast divider. So some researchers developed some fast divider algorithm like SRT division, but still requires the multiple steps. It is because the divider requires the comparison, and then based on the comparison, we need instruction or not. And then it's very hard to parallelize this operation. Okay. So for the RISC-V, so RISC-V supports the two whole instructions for division, like the div and remainder. So div generate the quotient of the division, and then REM generate the remainder of the division. Also, division can be performed for the unsigned number, like the DIVU or REMU. And then usually, if the dividend is divided by 0, it holds. It is error, like divided by 0, but this file does not prove the error. This is some unique feature of the RISC file issues. So it's over, time is over. So I will stop here, and then any questions? Okay, so thank you for your attention, and then see you in the next class.